Alright guys, just so real quick, this is an easy explanation. We talked about polynomials a little bit when we talked about diagnostics. The entire idea now is we want to talk about polynomials just as complete continuous variables, which you can do. We talked about transformations or using polynomials to deal with curvature. You can really build a polynomial as big as you want, but there's some other things we can talk about with interactions and things like that. So what I want to do is just to give you a basic example. You see this plot in your notes. I like the plot a lot. It's kind of straightforward. You see a minimum and a maximum. A lot of the times you only observe half this curve or start to observe the curve a little bit. You'd only see maybe a peak or maybe you'd see this downward trend from about, you could mark that at 1 or -1. You never really see the peak. Same way with with convex functions or functions that have a minimum. Concave functions with a max. Typically this is what people want to see. Regardless how you build the curves, whatever you do, it's something you really need to think about and what's going on with it. So there's really two types of polynomials. The first one I'm going to show you is just a very, very simple one. It's what we call a full second order model. What that means is it has quadratic terms associated with x1 and x2. It has x1 times x2, an interaction between x1 and x2. And I'll give you a feel for what this is. This is the cakes data. So x2 is the temperature in degrees Fahrenheit, and x1 be the baking time in minutes. So if I run this model, here's what we get. We have an intercept, we have x1, we have x2. Remember, this I means independent. You always need to wrap it around just in case you have, just in case, yeah. When you have quadratic terms or when you're making a transformation on the right-hand side, you'll see examples of that in the previous code or in previous modules where that's important. You have x1 squared, x2 squared, and then x1 times x2. Now, this is what we call a full second order model. You can fit it without this interaction term, but a lot of the times it makes a little bit more sense. So you go through, it's a quadratic, but what this x1 times x2 does is it allows you to model the boundaries. So it would give you an exponential growth or a jump. Y here is a taste quality. So it's what you're looking at, the average quality score of the cakes at a tasting. We know if something's cooked too short with cakes at a high enough temperature, maybe it can turn out okay. But if it's cooked too long at a really high temperature, it tastes terrible. So you can see that if x1 and x2 are large, it would have a negative effect. x1 times x2, think of 400 degrees at, just to give you an example, let's look at the data. You're talking about x2's 340 times x1 around 30 minutes. You can start to see how this would look and how it would work. So, just to give you an example of what the scale of that's going to be, 33 times 340, automatically you're at 11,000. It's going to move this if it's too high. So you need to understand how it works. You need to understand how too large of values will affect it, and that's what the squared terms allow us to do, okay? There's some interesting things you can do with these models, but what I really want to show you here is another thing. We have what we call raw polynomials and orthogonal polynomials. I can show you this real quick just to give you an example. Let's set it up where we just bring XP in, and XP is just 40 draws from a random uniform distribution from 0 to 1, and I've multiplied it by 2 to give it some spread. If I look at the correlation between XP and XP squared, that's at 0.96. Now, I want you to think about this for a second. Those are highly correlated predictor variables. And what you're going to try and do is you're going to try and interpret this like you would any other multiple linear regression. If we move x1 1 unit, leaving everything else constant, you can't leave it constant in this model, guys. So what we need to do is we need to go in and understand the effect of each one of these things. And that's what orthogonal polynomials allow you to do. It's very much a residual plot feel or added variable plot feel. An added variable plot, not a residual plot. An added variable plot feel of polynomial regression. So what you're going to do is you're going to account for the information that's already in the linear term when you fit a quadratic term. You're going to calculate, if you do a cubic term, you're going to calculate the effect of the quadratic and linear term and remove that and then calculate the cubic term. So there's a lot of different things you do. It's very much, like I said, it's very much added variable plot field. So there's ways to do this easily in R. I'm going to define YP to have this relationship. And then I'm just going to fit this M6. And I'm going to say I don't want to use raw polynomials. Raw polynomials are this model right here. I don't want to use raw polynomials. And I'm going to do something on the third degree, okay? So a third degree polynomial means a cubic. So we're going to run this, and you see here, you see everything comes back significant. Now, I fit this to be a cubic polynomial. If I come in here and I run model 7, take a look at something. What it says here, if you look at the raw polynomials, it says that every coefficient is significant. If you look at the orthogonal polynomials, that you're seeing in this model, what you're going to see is all variables are significant. If you look at the raw polynomial, the only thing it says is, hey, look, based on what we're seeing, only thing that matters is the cubic. Now, that might be the case for a lot of different things, but this talks to you about the effect of each level. This says the linear term matters, the quadratic term matters, and the cubic term matters. If you look at just the raw polynomial, all it says is the cubic term matters. And that's because it doesn't take into account the correlation that exists already. So these are things you need to think about as you move forward. And again, this will allow you to say, hey, all three pieces of this matter. All right. Now, again, this is just a different feel for the way it works. The predictions on both of these will be exactly the same. Nothing will change. It's just the way we allocate to do the hypothesis testing. All right, guys, let me know if you need anything.